Welcome everyone to this new appointment of the 40 under 40 lecture series on combustion. Today we are very happy to host Professor Pierre Brequigny. He obtained his mechanical engineering degree at INSA Rouen in 2011. His PhD thesis in 2014 was about the fuel influence of combustion in spark ignition engine, particular flame stretch, impact on the flame stretch. He had some time in Belgium. He was a postdoc at the Free University of Brussels, the Dutch-speaking one. And as of today, he's an associate professor at the University of Orléans since 2015. He is a member of the PRISM Laboratory in Energy Combustion and Engine Group, and his research focuses on renewable energy carriers and their effect on the performance and emissions of internal combustion engines, in particular ammonia, hydrogen, and I think their mixtures. And on this line, he will deliver a presentation on low carbon fuels from combustion properties towards engine applications. And Pierre, thanks again, merci beaucoup for accepting our invitation. And I leave you the floor for your presentation. Thank you.
All right. Thank you for the kind introduction. I'd like to thank the Belgian section for inviting me for those series. So today, as Alessandro said, I will talk about the low carbon fuels, their combustion properties, and how we can use them in engines. So to start with, I'd like to give a few words about the lab. I'm a researcher in the PRISM laboratory, which is a quite big lab in the University of Orléans because it is a multi-field laboratory. But in this one, there is a team which is called Engine Combustion and Motors team, where we are dealing with those fuel I just mentioned. So this is the people of our team. You may recognize some of them, especially our ammonia queen, Christine, or Fabrice, who are dealing with hydrogen fuel. So in this team, we have two main research topics. The first one, and the one I'm involved with, is about future fuels and how we can adapt the combustion modes in engine for those fuels. So we are dealing with a lot of different kinds. So for sure, hydrogen, ammonia, alcohols, various kind of gas. I would say most of them are renewable, and we try to use them with different kind of combustion mode that could be conventional, like gasoline direct injection, for example, or more advanced, such as dual fuel, rapid reactivity control compression ignition, or homogeneous charge compression ignition, for example. And there is a second topic in the team that I will not cover today, which is more about modeling, optimization, control, so developing control command for energy system or vehicles, also for those kind of fuels, and it is much more about energy management, I would say. So how we are doing our research in the team, it is mainly experimental. So we have two buildings where we have 9 engine test benches with 2 medium duty single cylinder engine, 2 high dynamic engine benches, and 4 single cylinder engine test bench that can be either with or without optical accesses, such as the one you can see here, sorry, which is quite unique, I would say. And when we to complement those experiments in engine, we have outside engine vessels, I would say. So for high temperature and high pressure vessel, to do laminar and turbulent burning velocity measurement, we have one rapid compression machine, as well as a rapid compression expansion machine, I would say, to study ignition delays, or premix flame as well. And we also have some vessel to characterize injection and spray development as well for liquid and gaseous jet. We use a lot of optical diagnostics, as you can guess, to apply to those techniques such as PIV, fluorescence, tomography, Schlieren, and so on. And on the engine test bench, we are also interested in the exhaust gas analysis, so using different kind of analyze. So where do we place our activities? Basically, we are really between the chemistry fundamentals data, so where we can find burner, GSR, or kinetic mechanism development, and the multi-cylinder engine, standard engine activity, where we are developing powertrain, testing the fueling system, the lubricant as well, or different combustion mode. And between that, we are covering from fundamental data like laminar burning velocity, ignition delay time measurement, the interaction between the flame, the turbulence, the effect of the aerodynamics of the engine on the spray mixing formation in the chamber or the ignition itself, and then try to characterize a bit the energy output of the engine using in-cylinder pressure measurement, heat release rate, and how this can affect the pollutant emission. And you can see some of our partners for collaboration below them, both academic or industrial. You can recognize one, Belgium, here. So this is a bit the type of data we can produce. So here you have first a laminar flame propagating. Here you have hydrogen jets. Here you can see some flame propagating inside in an engine together with the velocity field acquired using PIV technique. And this is a photo of a single cylinder all metal engine where we can get the heat release rate and the pollutant emissions. So basically, my research is using all of those experimental setup. It is more focused on premix turbulent combustion. So starting from the laminar burning velocity measurement using a combustion vessel, how then this laminar flame can interact with turbulence during its propagation and how it is accelerated by the turbulence or not. Then see how it can works in an engine. So because the flow field is much more different than in our vessel here, we also have very different condition in terms of pressure and temperature. And finally, how that affect the performances of engine, both in terms of, let's say, power output, efficiency, or emission. And we can have a look because some of this result can at some point be explained by the fundamental data or try to be correlated with the fundamental data, as I will show later on in my presentation. So how did I get my inspiration for this presentation? So I will start with two things that I liked. The first one is history. I'm really passionate about history, reading books, watching documentaries, and actually as a kid, I wanted to be a history teacher. So I'm a teacher, but not in history, it's not bad. And the second thing that I like, which was the point of this presentation, is Belgium. Not only to make those people happy, because I used to work with them, collaborate, discuss, and it's always a great pleasure, because also, as Alessandro said, I spent sometimes there in Belgium and I have the best memories there. So combining those two things that I liked, this is what we can find in the books. And I don't know if you are aware of this, but this is a coal gas ammonia fuel bus. So during the Second World War, due to diesel and gasoline shortage, the Belgian people had to convert their buses fleet to ammonia. And this worked quite well. And if we look a bit closer to what we have in that engine, actually coal gas and ammonia. So basically, these buses use all the fuels I'm currently working with. So it has hydrogen, it has ammonia, but it also has a mixture of hydrogen, CO, methane, which can be called syngas in our case. So this is basically the outline of my presentation. I will start with hydrogen, fundamental engine work, then ammonia, and then biogas and syngas with for sure a bit of ammonia because we are kind of ammonia lover in the lab. So let's go back to the future then. So as said, I will start with the hydrogen activity. So the PI of those activities, Fabrice Fauché. You can see different collaborators that worked on those recent years. So it is based on several industrial collaboration, but also national research on the project. So regarding the hydrogen engine, it has several challenges. First thing we can say is it kind of competes with fuel cells. And to compete with fuel cell, the hydrogen engine has to be zero emission, which is quite challenging. But using lean to ultra lean mixture, so very high lambda, if you prefer, you can reach almost zero NOx emission, as you can see from that figure here. Other challenges using that is to reach the high load. So at some point, you always need to increase a bit the equivalence ratio. You can also have the NOx or super NOx occurrence, even with those lean mixture. As you can see on this graph of in-cylinder pressure acquired in an engine here as function of the crank angle degree, and you can see this blue curve showing kind of super NOx, even with very lean mixture, and this was done in our lab. And also another challenge is the backfire, especially in the case of poor fuel injection, when at some point the flame goes back into the intake, which is critical in terms of safety. So this is how we worked a bit with hydrogen here in the lab. And for the presentation, we focus here on lean and ultra-lean combustion. So in this equivalence ratio range between 0.2 and 0.6. And here there are not that much fundamental data. So we worked in the lab on ignition delay times and try to see how kinetic mechanism can predict those ignition delay times, especially in engine-like condition. So as you can see here, for example, 80 bar of pressure, which is not very common. And I will not talk about it today. I will mostly focus on laminar and turbulent flame speed, which are more related to my expertise. So to investigate those laminar and turbulent flame speed, we have a combustion vessel in the lab, which is here. It has a 4.2 liters of internal volume. In terms of initial condition, the maximum are 10 bar and 200 degrees. Inside, we can find two tungsten electrodes that enables to ignite the gaseous mixture inside. And we can implement or not fans to generate an homogeneous isotropic turbulence zone inside the vessel to study flame turbulence interaction. In the case of laminar combustion, we only use one fan basically to mix the air with the fuel and to have really something premixed before igniting the mixture. And then we use optical diagnostics. So here an example is a double Z-type Schlieren viewing that gives us two planes of visualization of the flame and allow us to follow the flame propagation and then measure the speed. So how do we measure the speed? So from the radius evolution, we can compute, let's say, the propagation speed. And since the flame is spherical and expanding, it is affected by stretch. So it is something we have to compute as well. It is defined as follow, and it basically depends on the flame speed and on the curvature. So when we want to measure the laminar flame speed, we have to be at zero stretch. And it is not possible to reach that condition in our vessel, so we have to extrapolate the data at zero stretch. So you have here an example of the flame speed, the propagation flame speed as function of the stretch. So here you have the beginning of the propagation, which is basically impacted by the ignition, by the spark. So we have to remove that part. And then we have our experimental data. And as you can see, it does not reach the zero stretch. So we can use several extrapolation to go to this zero stretch point. The first one is called the linear stretch model, defined as here, where you can see the propagation speed at zero stretch, the stretch, and the LB parameter, which is very important here, which represent the stretch sensitivity of the flame. Basically, it is called the Markstein length. So this one is well appropriate for a mixture that are that have equidiffusivity, so a Lewis number equal to 1. But in some cases, we cannot use it because those some mixture deviates from Lewis number equal 1, especially hydrogen. So we can use a second extrapolation model, which is only based here on the curvature, as you can see on this term. And the last one is the nonlinear one, which is a bit more complex in terms of extrapolation. And it is well adapted for mixture that strongly deviates from Lewis equal to 1 and highly stretched flame. So you can see here the results of those three computations, and it gives very different results depending on the fuel and its properties. So at the end, basically, we need to recover the laminar burning velocity, and we only need the expansion ratio that is usually computed with an equilibrium computation. So how hydrogen flame looks like in our vessel. So you can see here 4 different equivalence ratio at different flame radius, so the flame propagating. And you can see something that is quite critical in terms of measurement. As you decrease the equivalence ratio, you can see that the flames start to show cellularities, instabilities. And this cellularities will make the flame accelerate, and then you are not really measuring a laminar flame anymore. So those cellularities are limiting the range of radius we can use for extrapolation. It can be a real issue in terms of measurement. So that's why it's difficult to go below that point, at least in ambient conditions, so 1 bar and about 300 Kelvin. But anyway, we try to measure the laminar flame speed. So our data here are in black, triangle, square, and circle for the different extrapolation I presented before. And you can see first that comparing our data with literature, we can see a lot of scatters, even in those regions where it's, let's say, possible to measure quite easily the laminar burning velocity, but you can see a lot of scatter. And we can see also differences with kinetic mechanism, so simulation, even at higher equivalence ratio. So for sure, the deviation is higher when you have low equivalence ratio. And this deviation is different depending on the extrapolation you are using. And we can see that the nonlinear one gets closer results to the kinetic mechanism, even though there is still big difference. So here up to 50% difference. So this is the first information we can get from those flame propagation. The second one is the Markstein length, so the stretch sensitivity of the mixtures. And basically to validate our choice of extrapolation, we can use theoretical model to compute this stretch sensitivity. So here there are two, one proposed by Zhengshen and the other one proposed by Bechtel and Matten. And if we compute them, we can see that the nonlinear extrapolation in red here gives better agreement with those theoretical model in terms of strength, especially with the Bechtel and Matten Markstein length model, sorry. So now let's move to turbulent condition and higher pressure. So here you have, again, different equivalence ratio, 3 different pressure from 1 to 4 bar, 3 different turbulent intensity from 0, so it should be the laminar case, but you can see that at some point you still get some wrinkles, up to 2 meters per second, let's say. And basically with high equivalence ratio, you can see that you keep a globally aspherical shape, although increasing the either the turbulent intensity or the pressure, you will increase the wrinkles. So basically you can see cellularities that are smaller and smaller and more present in the flame. Whereas if you look at very lean mixtures, you can see some very different flame morphology. If you look without turbulence, you can see here a flame that it is very buoyant. So due to gravitational instability, the flame rises into the vessel. And here you cannot properly measure laminar flame speed anymore. But also, if you increase the turbulence, you can see that the flame start to be highly disformed, stretched, not spherical, also conveyed in the flame, not staying in the center. And this is a very different behavior as you decrease the equivalence ratio. And to, let's say, study that, we used to present the Petersburg diagram, so which represent the turbulent intensity to the laminar flame speed ratio as function of the integral length scale of the turbulence to the flame thickness ratio. And you can then represent different regions in that diagram, which represent different combustion regime. So from wrinkled, let's say wrinkled and corrugated flamelets up to broken reaction zone. And you can see that as you decrease the occurrence ratio, you are moving left up in the diagram. But at some point we have a problem, because as you can see, there is no white data, because we are not able to properly estimate the laminar properties of the flame in those conditions. If you do a simple Contera simulation, you will get that order of magnitude for the laminar flame speed values, and especially the flame thickness, which seems a bit unrealistic if you compare to the flame you are looking at in the vessel. So we don't really know how to place those flames in the Petersburg diagram. The second thing we try to do in the vessel is to measure the turbulent flame speed and try to see if we can find some correlation that can predict this turbulent flame speed. And so those kind of correlation help us to understand which parameters influence the turbulent flame speed, but can also be used, for example, in CFD models such as the G equation. And here you can see a lot of data gathered. So basically here you have our experimental data in the vessel from Nicolas Villeneuve. So with the different pressure, occurrence ratio, and temperature, and data of the literature with very different fuels, so methane, hexoctane, ammonia, methane, or ammonia hydrogen blend, so covering a wide range of pressure, temperature, also Lewis number, and turbulent condition. And we can see that we are able to find something that gather all those data, with the turbulent flame speed being a function of the Karlovitz number, the Dam-Kohler number, and the Lewis number. So this is quite an interesting behavior. So this is exactly what I said. Question is, okay, this is a vessel, so a very controlled environment in terms of turbulence, pressure, temperature, but how this works inside an engine. So to study that, one of our other PhD students used an optical engine, spark ignition one. So basically, you have an optical axis on the piston that you can see here. So you can follow the flame from the bottom. The motion is a typical spark ignition engine motion, because it has a Pentloop cylinder head. So you will have a tumble motion that will break as the piston moves up and will generate the turbulence afterwards. We have a continuous hydrogen ejection placed here in order to have as much as possible an homogeneous mixture, in order to avoid any stratification and different occurrence ratio inside the chamber. And then we can follow the flame chemiluminescence using a filter, an intensifier, and a high-speed camera. We covered very different operating conditions. So it's quite low engine speed for a spark ignition engine, but due to the optical axis, you cannot increase that much the engine speed, otherwise you break it. The spark timing is quite standard, and it is also low intake pressure, a bit for the same reason as the engine speed, in order to not break and to not have too much, a too high load inside the engine. We can use then a couple analyses between what we can see from the camera and what we can get from the in-cylinder pressure sensor that will give us also the heat release rate and, let's say, the combustion phasing inside the engine cycle. So basically, from the images, this is typical type of flame image you can get from hydrogen combustion. And again, here you have the Petersburg diagram with all those different combustion regime. So here we varied the equivalence ratio from 0.55 down to 0.2. And as you decrease the equivalence ratio, same as before, you are moving up in the Petersburgian diagram. In region called the broken reaction zone, where basically you have a Karlovitz that is very high, and normally there is no CFD model that are really able to measure that. But looking at the flame, it just looked like, let's say, a very wrinkled flame, very distorted. So perhaps it is still, let's say, a flame that is propagating, perhaps with sometimes local extinction. We don't know because it's difficult with that diagnostics. And if you increase the equivalence ratio, you can see that the flame gets more and more spherical, which makes things easier in terms of diagnostics. And then we can go back to the turbulent velocity measurement, but this time in the engine with engine condition, both in terms of pressure, temperature, but also turbulence. And you can see that we are able to find a simple Zimont model, which is regularly used in CFD computation to compute the turbulent burning velocity. And one interesting thing is that we also observe that similar correlation, at least for lean mixture. So here, for example, from 0.2 down to 0.6 in the vessels, so which gives us a bit of confidence in that relation. It is interesting to see that we can find it both in the vessel and inside the engine. So this is most of the work done with hydrogen. I will now move to another fuel, which is also a hydrogen carrier, ammonia. So this is the main part of my presentation because we are now working on ammonia since 7 years together with Christine, with a lot of national, European, and collaborative projects. And I have to acknowledge here a Belgian colleague, Francesco Contino, because the momentum came from him. So just momentum speaking, a bit of word on ammonia. So there are more and more projects announced to produce renewable ammonia all over the world, both either in South America, in Australia, but also in Europe and Africa, and with very different scales. But for the moment, there is very few pilot facilities. If we look at the property of ammonia as a fuel, this is more challenging. So here you have a comparison of ammonia properties together with gasoline properties. And you can see that the heat of vaporization, so if you use liquid ammonia, is very high compared to gasoline. Its octane number is very high also, but this can be good for at least spark ignition engine, as you will avoid knock operation. And this is related also to the auto ignition temperature. But on the other hand, you have a very slow burning fuels in comparison with the gasoline, as well as the flammability limits that are very narrow in comparison to the gasoline. So the combustion might be quite challenging looking at those properties. Nonetheless, it is still a CO2-free, a CO3, and at least a PM3 at the exhaust, because ammonia can generate particles afterwards, but really from the combustion, you don't get those molecules. The drawback is that it is a fuel-bound nitrogen. You have a fuel-bound nitrogen, so which will lead to NOx emissions, so called the fuel NOx, not the thermal NOx, and also unburned ammonia. So a quick image of how a methane flame and an ammonia flame look like on a, let's say, regular burner, Bunsen burner. So you can see that it's very easy to have a stable flame with methane. Otherwise, you cannot stabilize it with ammonia. You always need the help of the pilot flame. So how do we do with engines? So when we started the work, we thought that due to the high octane number and the auto-ignition temperature, the spark ignition engine was an easier solution to use ammonia as a fuel. So idea is that either you can use it pure, so neat ammonia, is it possible? We don't know. Or due to those slow burning combustion properties, perhaps we can blend it with another combustion promoter. You have here a list of what we tested in laboratory, so methane, hydrogen, and alcohol. Another idea, still with the spark, is to go with a compression ignition engine due to its higher compression ratio that leads to higher efficiency, but use it with a spark and then favor the use of neat ammonia to avoid any other tank, let's say on a vehicle, which makes things easier. And what are the other way with a compression ignition engine, since it can, let's say, not ignite alone due to its high auto-ignition temperature? Use the dual fuel mode. So use a more reactive fuel that will ignite inside the compression ignition chamber and will then ignite the ammonia air mixture. And this is something else we tested in the laboratory. So presenting all those possibilities with ammonia engine, I will present some highlights of our results. First, starting with the fundamental properties, a bit of turbulence and combustion interaction. Then our results obtained with spark ignition engine, where our objective was, let's say, to reach the limit of operating condition with pure ammonia and see how we can extend those limits. And last, see how ammonia can be used in compression ignition engine. So let's start with the ammonia hydrogen blend. So first pure ammonia and then try to use blends of ammonia hydrogen or ammonia methane. So here you can see the laminar burning velocity. So it's 1 bar and 300 kbar as function of the equivalence ratio. You have the ammonia here, so you can see it's very slow laminar burning velocity below 10 centimeters per second. And as you increase the quantity of the promoter, so here it is methane, you can increase a bit its laminar flame speed. And this is what you can see here, for example, for lean mixture. And the different behavior adding either methane or hydrogen, where at the beginning up to 30, 40%, let's say 30%, both fuel has the same effect in terms of flame speed enhancement, but at some point you get a really exponential increase of the flame speed with hydrogen in comparison to methane that is more linear. How those flame looks like. So here you have stoichiometric 100% ammonia flame. You can see how slow it is, compares with 50% ammonia, 50% methane, and a 50% 50-50 ammonia hydrogen flame. So that is the first thing we noticed about the ammonia flame and how we can, let's say, improve it easily. But also adding those fuel will really impact the other properties. And again, we are here interested in the march time lengths, especially because it gives an idea of how the flame will respond to the turbulence inside an engine. So basically, when you add methane here, you decrease the march time length. So you are less sensitive to the stretch. And since you are getting closer to zero, you may favor a bit the propagation with the turbulence. But here with hydrogen, you even tend towards negative values of the march time lengths. And this means with turbulence, you will strongly enhance your flame acceleration. And this is a typical behavior of hydrogen addition that was also found putting some hydrogen into methane, for example. So again, we tried our theoretical model here to see if this behavior is correctly measured, let's say. And we found some agreements. So you have here lean, stoichiometric, and rich mixture. And we find some agreement between our experimental march time length measurement and those theoretical model, with the exception of this point. So pure ammonia 0.8 of equivalence ratio, which is a bit out of the trend, but we are currently investigating it again. And so here you can see basically that for lean and stoichiometric mixture, you can really get a negative value of the Markstein length due to the hydrogen addition. And why you get that? Because basically of the thermodiffusive behavior of the mixture. So in those two theoretical models, we can isolate two terms, this one for the Chen model and this one for the Bechtel and Matalon model that are represented here and here for both hydrogen addition on the left and methane addition on the right, and compare with the Markstein number, which is basically the Markstein length divided by the laminar flame speed. And we can see that this Markstein number currently follows, the trend follows the same trend as those terms, which represent the thermodiffusive behavior of the mixtures, since it has both the Lewis number and the Zeldovich number, which is related to the activation energy. And this helped us also to understand how it works inside an engine. So since ammonia has a very slow flame, the idea is to boost it with either hydrogen or methane. And the question is how this impacts the engine propagation. So here you have a graph of the CA50, so it's the timing where you have 50% of mass burn inside the engine minus the spark timing. So it is a duration in crank angle degree. And basically you can see that when you add hydrogen in your ammonia, you strongly shorten the combustion duration. Whereas with methane, you basically have something constant. Question is why? Because in both cases, you improve the laminar bending velocity, so you should be, let's say, faster with both promoter, but it is not the case. So let's see what the turbulence flame interaction says. So as you can see here, you have the laminar burning velocity for lean, stoichiometric, and rich, and you can see that both hydrogen or methane addition provokes the same laminar burning velocity enhancement. So it is not that lead to this engine behavior. So we moved back to the turbulent vessel, and you can see here our tubular flame. So here it's the double Schlieren view. So it is actually the same flame, but seen in two different views. So you have here neat ammonia flame, here ammonia with 15% of methane, and here ammonia with 15% of hydrogen. What we can see is that for the ammonia, you have something very distorted with very big structure, elongated, let's say, tongue. You can see at some point some extinction occurring or flame that are detached from the main one. You can also see that kind of behavior here with the methane addition. So both are quite similar. Whereas for hydrogen, you still have something very disformed, but you don't see those flame detachment or flame extinction. And if we look at the turbulent to laminar flame speed ratio, you can see that when starting from neat ammonia, when you add hydrogen, you have a strong enhancement of this ratio. So meaning you are increasing the turbulence flame interaction up to a certain point. So here up to 10%, because after at 50%, you start to decrease it again. Whereas when you add ammonia, you directly decrease this ratio. So meaning that your turbulent flame interaction is weaker. And this is basically related to the effective Lewis number, so the thermodiffusive property of the mixture, and the experimental Markstein length, as we can see from those trends. Okay, so now we are able to understand a bit how the ammonia flame happen inside the engine, how it interacts with the turbulence. But what do we have in terms of performances and emission? So our first experimental campaign was done with a regular, let's say a commercial spark ignition engine, completely unmodified. We even kept the original pistol geometry, which was designed for gasoline direct injection. And we tried to see what we can get from those experiments. So you have here maps of IMEP and down here the indicated efficiency. So the IMEP is basically the power output of the engine. So we have here a different equivalence ratio for different hydrogen addition for two different intake pressures. So first, we can see that we can get an IMEP that is similar to what we can get from methane air combustion, which is good. And this for both intake pressure investigated. And we can see that increasing this intake pressure gives you higher power output as expected, but it also gives you higher efficiency, as you can see from those two maps. So looking at where we get the highest efficiency, it is basically for lean mixture, so below 1, so here the red zone. And also it is not necessary to add that much hydrogen. So below, more than 20% is not necessary in terms of efficiency, because after you start to decrease again the indicated efficiency. And in terms of value, so we are able to get more or less 40%, a bit less, which is similar to other fuels such as methane, for example. So here, ammonia is surprising us in terms of performances. In terms of combustion phasing, so you can see here the combustion duration for different combustion phases inside the engine. So here you have 10% of mass burn minus the spark timing. Here it is, let's say, the flame propagation phase. So 50% of mass burn minus 10% of mass burn timing. So it's again duration in crank angle degree. And here the total combustion duration. And starting from the neat ammonia, here it is the red point. So we were only able to do a stoichiometric condition in this in those experiments. You can see how adding hydrogen strongly decreases the combustion duration, and especially the first phase here, where hydrogen has its biggest impact. So this is how we are able to get better performances with hydrogen. Looking at the emission, this is the big drawback, because we have an acceptably high ammonia unburn at the exhaust, so about 1% here, as you can see. And plus, the trend with NOx is opposed, so a bit similar to NOx and HC or CO with conventional hydrocarbon fuels. You have here a trade-off between ammonia and NOx, so when you have low unburned ammonia, you have high NOx emission with, again, very high level. So mitigation strategies are clearly needed here, either using SCR, so selective catalyst reduction, or an ammonia catalyzer, for example. But this is an activity that is not covered in our lab. Another emission that is important when you deal with ammonia is the N2O, because N2O has a global warming potential that is 300 times higher than the CO2. So here we measure less than 100 ppm, which is equivalent to about 1 to 2% of CO2 at the exhaust. Okay, so as you can see, operating with neat ammonia is quite challenging. So we try to extend a bit the condition and see where the limits. So here we studied 3 different equivalence ratio: lean, stoichiometric, rich, iron stoichiometry still, 4 different engine speed from 650 RPM up to 2000 RPM, different intake pressure, so to have different engine loads. So below atmospheric 1, so below 0.65, about 0.8 and 1 bar at intake pressure, and try to have minimum hydrogen addition, so up to 10%, because as we saw before, not necessary to go to have more than that to not decrease the efficiency. So here, where we don't have any crosses, is the condition that we were not able to run with stable operation in the engine. So you can see that at a low and high engine speed, running on neat ammonia is difficult. The other problem is the low load. So when you decrease the intake pressure, you cannot run on neat ammonia, and even sometimes 5% of hydrogen is not enough to get stable operation. You have to go up to 10%. Okay, the question is, how do we push back the limits with ammonia? So our first idea was to take advantage of the auto-ignition resistance of ammonia. So we chose to use a diesel baseline engine, removing the diesel injector and put, let's say, I'm a bit simplifying, but put instead of the injector a spark plug. And this engine features a compression ratio that can be varied from 14 to 16, so much higher than the conventional spark ignition engine we use. And the first thing, if we look at the combustion duration, so you have here the bar graph representing the different combustion phases as I presented before, you can see that increasing the compression ratio inside that diesel baseline really decreased the combustion duration, a bit in the same way as the hydrogen does inside the conventional spark ignition engine with the shaded bars here. So this can be a good point. And if we look at the low load limit, so you can see here, this was our limit with the spark ignition engine with 10% of hydrogen. So this was 3 bar of IMEP with a minimum intake pressure of, let's say, 0.55. Whereas in the diesel baseline, in this SACI engine, even with the lowest compression ratio, the load was already lower than what we get in the spark ignition engine. And increasing the compression ratio allows to even decrease more this low load step, so down to 2 bar of IMEP with a 0.4 intake pressure. So this is quite interesting features of the increasing the compression ratio. Problem is, again, the emission. So you have here the NOx ammonia trade-off. What we can get from the conventional spark ignition engine without any hydrogen, and what we can get from the spark assisted compression ignition engine. And you can see that we increase a lot. We are shifting the ammonia NOx trade-off towards higher unburned ammonia, mainly because we have ammonia that is trapped inside the crevices of the engine because of the port fuel injection and the squish region. Okay. Another possibility to extend those operating limits is to use partially cracked ammonia. So we saw that hydrogen is a good way to extend the operation of the ammonia engine, but we cannot think about adding hydrogen with, for example, another injection system or another tank. So a good way could be to crack the ammonia online, so using the principle of this reaction. And so basically you just need heat to provide that. So you can use catalyzer, catalytic converter that can do that. And you can use, for example, the heat from the exhaust gases that will allow you to crack the ammonia here. And this was actually done by Comotti and Frigo in 2015, where they put an ammonia cracker online in the engine, and they were able to achieve 98% of ammonia conversion. So we reproduce that, but without the cracker, so reproduce the gas composition. So either, so let's say a partially cracked mixture, so composed of ammonia, nitrogen, and hydrogen. And this is the benefit we can get. So you strongly increase the laminar flame speed. So here starting from pure ammonia and then cracking it up to 40% of cracking. No, 60%, sorry. And you can see how it decreases the combustion duration again. But you have some penalty doing that cracking. So first, you decrease the power output for all equivalence ration. although it is a slight decrease. But you also decrease the indicated efficiency, especially if you consider, and this is the curve 3 here, especially if you consider the energy required to crack the ammonia. So this may be, this is a clear drawback of this solution. What about the turbulent flame speed of those partially cracked ammonia mixtures? And also how do we enhance the laminar flame speed as it is not exactly the same as just blending ammonia and hydrogen, since you have a bit of nitrogen in it. So starting from 5% of cracking up to 40% of cracking, you can see that you both increase the laminar burning velocity here, but you also shifted its maximum towards richer mixture due to the presence of hydrogen. So this is without any turbulence. Then we add turbulence. And what we can see is that for lean and stoichiometric mixture, you have an enhancement of the flame speed. So let's say that your turbulent flame speed is either higher than your laminar flame speed, which is expected, but it is not the case on the rich side. So you have little to no flame speed augmentation there. And basically, this is again due to the thermodiffusive property of the mixture, and especially the Lewis number that is due to the diffusivity of hydrogen that is enhanced for lean mixture. And here, if you look at the turbulence effect, you can really see, so for 3 different turbulence levels, how it is much more affecting the lean mixture in comparison to the rich mixture. So again, the partially cracked ammonia is not a straightforward solution. So the last thing we try with those spark ignition engine is to use another kind of fuel. And ethanol was good for us for several reasons. First, it has a high laminar burning velocity. And so we studied the improvement, the enhancement of the ammonia laminar flame speed here, adding ethanol in it. So you can see here at 1 bar and 423 Kelvin how you can enhance. So from, let's say, 10 centimeter or 15 centimeter per second up to 70 centimeter per second. So you can really improve these combustion properties. And we also studied how pressure and temperature in another vessel, how pressure and temperature simultaneously affect this laminar flame speed. And again, here you can see that a small addition of ethanol can really give you a big gap in the laminar flame speed. And the other interesting property is that ammonia and ethanol are fully miscible. So we prepared a mixing test bench where we looked at the ammonia ethanol mixture, and you can see here on the liquid part, you only have one phase. Whereas if you try to mix ammonia with gasoline, you can see that you have 2 phases and you have higher, even with higher pressure. So you are not able to properly mix. So this is a good feature of ethanol, since you can then imagine a single tank and a single injection system for an ethanol ammonia blend. What about the engine? So we try then, as it is only one liquid, to use a direct injection. And it was the first data on direct injection for liquid ethanol ammonia blend in a spark ignition engine in comparison to pure liquid. We tried 2 different injection strategies. An homogeneous one where basically the mixing is really introduced early in the blend, and a stratified one where you have a later injection, so let's say in the middle of the compression stroke. So if you look at the thermal efficiency, you can see that you can get almost 40% of efficiency, and similar to methane. So methane was here our target because we wanted to get the same power output as stoichiometric methane. So that's how we set our blends here from pure ethanol to pure ammonia. So basically, the homogeneous strategy gives better efficiency, a lower fuel consumption then, and lower NOx and CO emission for all blends of ethanol-ammonia. The stratified is able to produce shorter combustion duration and lower NOx, and CO emission for pure ethanol at least. And there is no particular effect on the unburned ammonia between both strategies. We can only see that increasing the amount of ammonia in the blends will lead to higher unburned ammonia again. So what we can say is that up to 50%, we can really have a positive effect of ammonia into the ethanol blend, both in terms of thermal and combustion efficiency, let's say, but we have to take care of the NOx and CO emission, especially in the case here of the stratified strategy. And the direct injection with pure ammonia was quite challenging because we really had to advance strongly the injection. So, for example, for the blend, it was always at the beginning of the compression stroke, but for the pure ammonia, it was at the beginning of the admission stroke. So we try a split injection strategy, and it was then feasible to run on the pure ammonia with direct injection, but it was very constrained, and the duration, the phasing range is really restricted. So it's quite a challenging operation. And it has to say, so not an expert into that, but I have to acknowledge colleagues that work also on that, so on ammonia spray. The ammonia liquid spray has particular properties. So you can see here a comparison between the ammonia injection, gasoline, and ethanol for a different density condition at low and high temperature. And you can see, especially at low density, that the ammonia spray is really narrower, and the penetration length is then higher than for gasoline and ethanol. With higher density, so let's say higher pressure in the medium counter pressure, the spray looks similar for all the three fuels, although you can see some different, something a bit different still for ammonia. And you have also this effect of the really higher heat of vaporization of ammonia that will affect the temperature inside the engine, actually. Okay, if we look how it burns inside the engine, and this was our first visualization of the ammonia flame in the optical engine, we compare two modes. So this is what we used to do at the beginning, so conventional spark ignition combustion. So you have here the spark, perhaps, sorry, they are not titled, so I will show it again. You have here the ignition that starts from here, and then you have the flame propagating this way. Whereas here we try something different. We use a more reactive fuel to ignite the ammonia air mixture inside the engine. So in a compression ignition mode, let's say, so a dual fuel operation. And this is the type of in-cylinder pressure signal you can get from that. So what we can see is that with only 11% of decay in energy to ignite this, we were able to get similar MEP than with the conventional spark ignition engine, even a bit higher. So here, we then thought that the dual fuel RCCI operation was a good opportunity. So we investigate various injection strategy for the ammonia RCCI engine, this dual fuel engine, for decay. So we have a single injection of decay with the minimum quantity allowing stable operation. The same, but just a little more, and then two different split decay injection, an early one, so one early, one late, and two late splitted injection. And we can see that it was possible to run with a diesel energy fraction, so a decay energy fraction below 2%, which is quite impressive with a really stable operation. And what we can see is that the minimum diesel amount is not always, let's say, the best operating condition, because you can see that adding just a bit more, you can get really higher efficiency. And also having a splitted injection strategy seems to be a better strategy to get both higher efficiency, but also allowing to decrease the diesel quantity in order to decarbonize as much as possible the engine. So here the best splitting strategy for the decane seems to be the Lates split for both performance and emission, especially if you look at the N2O emission here, where with both the minimum single injection of decane and the early split injection, you have more than from 80 to 160 ppm of N2O, whereas the late injection split strategy gives very low N2O emissions. Okay, so this is, I would say, almost done with ammonia, because I will still keep some ammonia on that part. So the last low carbon fuel category I would like to present here is about biomass gaseous fuel. Because biomass can represent a real alternative for combustion system, especially, let's say, for CHP power plant. And we can see that it is for an increase of the biomass share in the energy mix is forecasted. How do we get energy from biomass? So let's say to have gaseous fuel, so you can either use gasification, which will produce a syngas or producer gas containing H2, CO, methane, carbon dioxide, and nitrogen, or you can use anaerobic digestion, which will basically give biogas. So for sure, in that case, you can after use a Fischer-Tropsch to get a synthetic fuels, a liquid one. But here I will only focus on those gaseous fuels. It is also interesting to know that both processes can produce ammonia, especially gasification that can lead to impurities such as we know, ashes, tar, char, HCN, H2S, and also ammonia, especially when the feedstock is nitrogen rich. So when you have, for example, manure or sewage sludge. And it is mostly removed before combustion, but with a supplementary cost. And this is a short review of what quantity of ammonia you can expect in the producer gas. So sometimes up to 6%. So it's small, but you cannot neglect it. And the question is, how can this ammonia quantity can impact a genset application, or let's say a combustion engine in its operation? So then we proposed a project that was funded by the CNRS called Mass Symbiose, where we mix ammonia together with biomass gaseous fuels. So the idea is you have a nitrogen-rich feedstock. You either use anaerobic digestion or gasification. You get a syngas or a biogas that can contain some ammonia, and at some point you can even mix it with, let's say, a renewable ammonia, depending on your feedstocks. So the objectives in that project was to study the fundamental combustion properties of various biomass fuel compositions, so various syngas and biogas composition, studying both laminar burning velocity and stretch sensitivity, mixed with ammonia at some point, and then investigate how those composition and adding ammonia in it can affect the engine and emissions, engine performances and emissions, sorry. So I will present as before, first fundamental combustion properties and then engine results. So if we look a bit on the properties of the blend that we investigated, so we selected here 4 different syngas composition and 1 biogas composition. So you have here the different components. So Regarding the syngas, they have more or less hydrogen, more or less CO. They are more or less diluted, in some cases up to 70% of nitrogen CO2. This is very, let's say, bad quality. All of them have similar molar mass, a bit higher than the ammonia one. If we look at the density, stoichiometric air-fuel ratio, they are all those syngas composition are similar, but with really a lower stoichiometric ratio than the ammonia and the biogas. If we look at the energy content, so for sure the LHV, both mass or volume LHV for the syngas are much lower than the biogas and the ammonia. But if you compare that on an energy per meters cubed of air basis, they are all similar. So it is possible to burn this in an engine. It will give you a power output that is reasonable. And if we look at what can be the effect of adding ammonia to the biogas, basically no big change from those bar graphs. If you're adding it to syngas, you will probably increase a bit the energy content and the stoichiometric air-fuel ratio. So what about combustion properties? So first, laminar burning velocity as function of equivalence ratio. So this is basically a 1 bar and 300K experiments. So you have here, again, the pure ammonia with its very low burning velocity and the different syngas composition and biogas in between here in black. And you can see how the composition can affect these properties. The most diluted one, the fluid bed composition, is here, whereas the let's say the biogas here and the updraft are quite similar. Biogas and updraft 2 here, sorry, are quite similar. If we mix ammonia with biomass gaseous fuel, adding ammonia will surely decrease the laminar burning velocity, but in terms of stretch sensitivity, it will not have big effect. So the main effect for the engine will probably not be the turbulence flame interaction, but the laminar flame speed. So this is what we try in our engine. So mixing this syngas with a bit of ammonia. So here we can see that we can increase the power output, but need to advance the spark timing. We decrease a bit the indicated efficiency. We slower the combustion duration as expected from the laminar flame speed properties, as with the previous fuels. And the most interesting part is on the emission. So especially the NOx here in orange, as soon as you get a very small quantity of ammonia in your syngas, you directly get 2000 ppm of ammonia at the exhaust. And this remains constant after, even if you add more ammonia. And also in terms of combustion efficiency, so if you compute it based on the hydrocarbon and CO emission, you can think that it is a constant one. But basically here we were not able to measure the unburned ammonia, so we had to use the oxygen content to compute another efficiency. And you can see that here you will decrease the combustion efficiency adding ammonia, meaning that there is surely unburned ammonia at the exhaust. So to conclude the presentation, the hydrogen is a nice opportunity for transport, but it has several challenges to address, especially characterizing the fundamental properties for very lean mixtures, studying the effect of intrinsic instability, so due to thermodiffusive properties, also studying the effect of steam dilution, which is quite used for engine to avoid any backfires or a knock. The ammonia, regarding the ammonia, it has an easier storage. It is an easier storage compared to hydrogen, but the combustion is quite challenging, and we need to tackle the limited range of operation and the ammonia slip, and better understand the turbulence flame interaction. Regarding biomass gaseous fuel, we can have very different composition, and there is a question on how those compositions affect the properties in terms of burning velocity, stretch response, thermodiffusivity, and how also the important dilution level and the dilution component can affect that. Although there is no major modification when you have a bit of ammonia in it, and then it can be used in an engine as it will lead to higher power output, a slower combustion, and therefore a lower efficiency, and you have a problem with emission with both NOx and unburned ammonia. So thank you for your attention and for the invitation again, and best wishes for the end of the year.
Thank you, Pierre, for this very interesting talk and lots of information, lots of interesting results. So yeah, thank you again. And we are open now the Q&A session. So if anyone from the audience has any questions, please feel free to unmute yourself and ask Pierre your questions.
Hello,
Okay,
this is Mustafa.
Yeah.
Go ahead. I have a question about the effect of turbulence on the flame speed that you mentioned in the ammonia part. And before that, you talked about a flame stretched in the hydrogen part. And so turbulence under normal condition usually stretches a flame and thus has a thinning effect on it. This affect the flame speed as well. So my question is that, is this a monotonic relation where turbulence only has a thinning effect on the flame, or is it also possible that at very high turbulence levels, when small eddies can penetrate into the reaction zone, could also have a thickening effect on the flame and thus affect the flame speed in a different way?
Yeah, although we cannot observe that in our vessels. But if you look at the Petersburg diagram, it is true that increasing the turbulence level will lead to very move your points at the top of the diagram. Perhaps I can show it back. Sorry. So here, for example, so you will move at the top of the diagram. And here you can have extension, as you say, perhaps thickening, and the flame might be completely different. But I cannot tell how, because I cannot observe it. And there is another thing that can happen when you increase the turbulence. At some point, you're getting smaller and smaller wrinkles, so that your turbulence scales become smaller and smaller. So you wrinkles more and more the flame, but at some point this has a limit, and your wrinkles will recombine to bigger one. And then your flame surface is then decreasing. And so the flame speed, the turbulent flame speed enhancement is decreased as well. I hope I answered the question.
Yeah, thank you.
Thank you, Mustafa. Are there any other questions? If not, I just have a more general question regarding the future of internal combustion engines. If you have your perspective, I mean, might be a biased perspective, but I'm really curious to see if the research that will go on. You tried, you've shown us different injection methods. If you have been thinking about these new fuels will also change the way like the engine will is designed, and the way the process, the cycle is preside. I've heard about 3-stroke engine rather than 4 strokes. I'm just curious about your take on this matter.
Okay, so I cannot tell about, let's say, 3-stroke or even 5-stroke engine. I know that it exists. I don't know if it can apply to those new fuel. Perhaps it could be interesting to investigate. What is surprising from our first test, here we're like, okay, it was possible to use regular engine, non-modified one with very different fuels from what it was designed for. And this was quite surprising. So there is for sure rooms for improvement and optimization there in chamber design, possibly aerodynamics, so motion, in-cylinder motion design as well, to improve the combustion with those fuels. and mixing as well, for sure.
Okay, so well,
in the future, difficult to tell. Fact is, we clearly saw in our research a diversification of all the fuel we tested. So here I presented hydrogen, ammonia. There is a lot of momentum on the methanol as well, or fuel like DME for this.
DME, yeah.
And yeah, perhaps I don't know if the engine can be multi-fuel or if we have to find a single engine for a single fuel each time, but yeah.
Okay, yeah, and so there's still hope for internal combustion engines for sure. Open. Okay, thank you very much, Pierre. If there are no other outstanding questions, I will close the session, and I will thank you again for this presentation. And I also join you in wishing everyone and then all yourself happy holidays and a good end of the year. And see you next year with new appointments of the 40 under 40. Thank you, everyone.
Thank you. Bye-bye.
Thank you.